Well, hi everybody. So back again. Last sessions we did, I believe RL and RC source-free circuit. Today we will work on first order circuit with forcing function. Okay. Before we go into the circuit, I will review a little bit on the first order differential equations, how to find the solutions. So let's look at the general form of the first order differential equations. Okay, so therefore it's in the form of dy dt. Of course, y is a function of t. Okay, plus a y function y equal to a forcing function f of t. Okay. Before, in last sessions, f of t was equal to 0 because we have no source. It's a source free. Okay, become homogeneous equations. Well, if you have this form of equations, okay, the solution to these equations, to 1, okay, is in the form of y of t equal to, it consists of two functions, yn of t plus yf of t, okay, where yn of t, okay, is the solution to the homogeneous equation, which means it's dy dt plus ay equal to 0. That is, you set your forcing function f of t equal to 0. Okay. Another one, there's another solution is yf. Okay, it's a solution to the actual differential equations. So therefore, you have to solve dy dt plus ay equal to the forcing functions that you have. I believe in mathematical term, if you learned in your math class, okay, this is called the complementary function of solutions, right? Complementary solutions of functions, and this one is the particular solutions. That's in math class. Okay, well, we're going to solve for yn and yf, but to start showing the easiest so-called solutions, and also represent us as a DC in electrical our electricity class. So therefore, I'm going to let f of t equal a constant a. Okay, a constant. Okay, so therefore, okay, we have to solve two equations. One is dy dt plus ay. Let me put n here as in to represent that, well, this formula is to solve for the the yn, okay, equal to 0, okay, because we have to set it f of t equal to 0 for this case. Okay, and another solution that we have to solve is, of course, dy f dt plus ayf equal to f of t. All right. So let's start with yf of t first. Okay. Well, I'm just going to jump into the solutions. Okay. So therefore, we're going to let. Okay, sorry, if f of t here, we say that it's equal to a, so this become a. Okay, so actually I'm gonna give you later on a table, okay, a table of what the solution for yf to be, okay, to try. So yf of t in this case, I'm going to let it equal to also a constant k1. Okay, so if you have f of t is a constant, we're going to assume that our solution yf is also a constant. Okay, so therefore, we're going to substitute it back into the equation itself. So therefore, dk1 dt plus ak1 equal to a. Well, dk1 dt is a constant, so therefore this is 0. So therefore you would have k1 equal to this, which is another constant, some constant. Okay, it's a constant. So that means your yf of t, your answer will become a constant values, k1, okay, a over a. Okay, well, back to the homogeneous equations. Okay, in this case, right, well, we actually, this is what we did for the source-free circuit. So therefore, you can use the separable variable. So you would have dy, right, over dt equal to minus a yn. So therefore, separate the variable, yn come to one side, and of course, dt jump to the other side of the equation, equal sign, right? Integrate both sides, right? So therefore, you would get yn of t equal to some constant k2 e to the minus at. Okay, so therefore, this is your yn and this is your yf. So therefore, your final solution for this equation, first order differential equation, consists of the sum of both of them. So you would have yf of t plus yn of t, or equal to y of t equal to k1 plus k2 e to the minus at. So this is the general solution. Okay, well, in electrical engineering, okay, we have names for these solutions. Okay, well, k1 we call it the force response. The second term, the yn, k2 e to the minus at, we call it the natural response. Okay, so the difference are, well, if you look at the natural response, you can see that there's e to the minus at, and the shape of the e to the minus at, right, is that it decays, right? It decays down. So therefore, we can describe the natural response, which also has another name, which is called the transient response. Okay, it's defined that it is a circuit temporary response that will die out with time. So that's a natural response or transient. Okay, but the force response, or in another name is we can call it the steady state response. Okay, is the behavior, it will show the behavior, okay, of the circuit, okay, a long time after the excitation is applied, and external excitations is applied to the circuit. Okay, so at steady state, what does the response look like? This is your force response or the steady state response. Okay, so therefore, I'm going to give you an example, two examples with the capacitor and inductor. Okay, so therefore, let's start. Well, for the RL and RC, for RC circuit, source free, we say that our equation that we got is called the discharging equations. So in this case, we're going to do what is called the capacitor charging equations. Okay, so let's say that, okay, well, I'm going to say, let's say that at t greater than 0, okay, my circuit start to look like this already. So RC circuit, but in this case, there is a voltage source connected to it. And I'm going to assume that before this, okay, the switch was moved at t equal to 0 with VC at 0 has some value V naught in it. Okay, so this is at t greater than 0, right? We have this circuit. Okay, so I'm going to start, well, it's only one loop, right? So current flows like this. I'm going to set current flow like this in this case. Well, passing through R, so there's a positive or negative voltage drops, VR, and then go through the capacitor, so positive. The current go into positive, leaving a negative of the voltage drops. Okay, so write down KVL of this mesh, of this loop, mesh or loop. Okay, we would have Vs would be equal to VR plus Vc. Okay, VR plus Vc. Okay, now, but of course, VR is equal to R times I. Correct? So you would have, therefore, Vs equal to R times I plus Vc. We want to know, the final answer that we want to find is what is V across the capacitor. Okay, well, let me write this. Find Vc of t. Okay, find Vc of t for t greater than 0. Okay. So, but then, it's Ri. I is still not in the form of Vc. So, is there any link or relationship that you can see? Right, linking the current I, right, towards Vc. So I hope you can recall the formula relating the current, right, that go through a capacitor and the voltage drop across a capacitor, and that is I equal to C dVc by dt. So therefore, I'm to substitute the current I in there. So you will get Vs equal to RC dVc dt plus Vc. Okay, right? So therefore you will get, rearrange it. So it would be in the form of first order differential equations. You would have dVc dt plus 1 over RC Vc equal to Vs over RC. So therefore you've got your equations. Now we need to solve for Vc. So I'm going to start doing this. So let's see. So let's go dVc dt equal to, right, Vs over Rc minus Vc over Rc. Or in another word, I can write it as minus Vc minus Vs over Rc. Okay, so therefore the unused, separate variable again. So you have Vc minus Vs equal to minus dt over Rc. Okay, so integrate both sides, right, from t equal to 0 to t. And if we say that Vc at t equal to 0, there's some initial conditions, some initial values already there, which is V naught. And this is at t equal to t, it's some we don't know yet what it is, so write down as a variable Vc. Okay, so therefore when you integrate this, you would get ln Vc minus Vs, right, from V naught to Vc equal to minus t over Rc from 0 to t. Therefore, you get ln Vc, right, minus Vs minus ln V naught minus Vs equal to minus t over Rc. Okay, so subtractions, ln and ln minus each other, you can write it as ln Vc minus Vs over V out minus Vs equal to minus t over Rc. Okay, get rid of your ln, so you take the exponential across the border. So therefore you get Vc minus Vs over v naught minus vs equal to e to the minus t over rc. Okay, and of course if you recall from our last topic, last sessions, tau, right, is equal to rc, your time constant. So we can write it as vc minus vs over v out minus vs equal to e minus t over tau. Okay, so therefore vc minus vs is equal to v naught minus vs, okay, e to the minus t over tau. And so therefore vc of t would be equal to vs plus v out minus vs e minus t over tau. So therefore you get your answer. Okay, this is for t greater than 0. Okay, so for a complete answer you will write, well, vc of t would be equal to v naught, right, for t less than 0. Okay, and it is vs plus v out minus vs e to the minus t over tau for t greater than 0. So this is a complete response. Okay, so there it is. Okay, so this is how you actually in general analyze the circuit. Okay, later on in the next sessions you will learn a shortcut. You learn a shortcut of how to analyze a circuit, without having to derive everything. Okay, so the next one I will do, okay, is RL circuit. RL, so let's look at example, well, exercise example. So RL, and of course there's a vs. So we're gonna assume in this case, that there's some switch changing at t equal to 0. So a switch change at t equal to 0, and the current IL, okay, at 0 it's I naught. Okay, so therefore this is IL, right? So when the switch change position, you get this circuit here. So this is like t greater than 0. Okay, so I'm going to find IL. What happened to IL? So I want to find IL of t for t greater than 0. Okay, so therefore it's a loop again. So I'm going to just guess and, well, just do the KVL. So I going out from the source, go through R, go through L. So that means this is also IL, right? IL enters R, pass through R, result in a voltage drop like this, plus minus, and also induce a voltage across L like this. So therefore KVL for this loop is, of course, again VR plus VL equal to VS. Let's see, I want to find I, right? So I have to change everything into I, change to VR to I. So Ohm's law, right? V equal to IR, so R times IL, okay, plus VL, the relationship between the current going through V and the induced voltage across L is of course L di by dt. Let me rewrite this, it's not so nice. So R times IL, so this L dIL dt equal to Vs. So rearrange it to make it look more like a first order differential equations. You will have dIL dt plus R over L IL equal to Vs over L. So therefore your first order differential equation for this case. So we're going to solve for IL. So we're going to do sort of like the same, similar to what we did with the problem above. So therefore dIL dt is equal to Vs over L minus R over L IL or equal to R over L times Vs, right, over R minus IL, this, okay. So therefore DIL dt, right, become equal to minus R over L times IL minus Vs over R. So separable of variable, so therefore DIL over IL minus Vs over R equal to minus R over L dt, right? So integrate both sides, right, from 0 to t, and we say that at t equal to 0 there is initial current in an inductor I naught, and this is a value that we don't know yet at any particular time t. So when we integrate this, you have ln IL minus Vs over R, right, from I naught to some IL equal to, right, minus R over LT from 0 to t. So therefore you get, so therefore ln IL minus Vs over R minus ln I naught minus Vs over R equal to minus R over LT. Right, so therefore ln IL minus Vs over R divided by I naught minus Vs over R is equal to minus R over LT. Right, take the exponential across the equations, so you have IL minus Vs over R, right, over I naught minus Vs over R equal to e to the minus R over LT. Okay, so therefore IL minus Vs over R equal to I naught minus Vs over R e to the minus R over LT, right? Well, and therefore IL of t equal to Vs over R plus I naught minus Vs over R e minus R over LT amps. So therefore that's the final answer for t greater than 0. Okay. Now I'm going to show you something between these two formulas that we have achieved. Okay, the first one was, the problem was like this, right? Plus minus Vs R C, right? See like this, right? This is Vc, okay? And the answer was Vc of t equal to Vs plus V naught minus Vs e minus t over tau or Rc, right, volt. And in this case Vs, right, Vs, and then we have R, right, this is IL, this is L, okay, and the answer is IL of t equal to Vs over R plus I naught minus Vs over R e minus R over LT. Or actually we can say that, well, for us tau is L over R, right? So therefore if we say that tau for our time constant is L over R, therefore our IL of t is equal to Vs over R plus I naught minus Vs over R here, E minus T over tau. Okay. Now, let's look. Okay. From both of them, if I write down Vc of t again, Vs plus V naught minus Vs, E minus T over tau, right? Okay, let's look. Well, let's look at this term here, V naught and I naught, right? These two values were our initial values, correct? So this is our initial values of the voltage capacitor voltage and inductor current, initial value, right? As a switch move, in this case t equal to 0. Okay, well tau, right, with tau, so it's minus t over tau, right? So if it's RC, tau is equal to R times C, right? Or if there's more than one R, it's R equivalent, right? R equivalent times the capacitance values. For the RL circuit, right, tau is equal to L over R, right? Again, if there's more than one resistor, then we have to calculate equivalent resistor or the Thevenin resistance of the circuit, looking from the L and then from C. Okay. Then there's these values right here. See, there's Vs right here and Vs right here. And there's Vs over R right here and Vs over R right here. So what this value is, okay. Well, let's see. If I ask you to find, this circuit right here, this circuit right here, at t equal to infinities. So at t equal to infinities, right? This is your circuit. If the circuit has been like this for a very, very long time, t equal to infinities, right? From our policy, our rules for DC circuit, right? If there's no changes in the voltage in the capacitor, or in other words, if the capacitor is fully charged, okay, so we can assume that at t equal to infinities, our capacitor is fully charged. Our capacitor will act or behave like an open circuit. So therefore, at t equal to infinities, if you have to analyze the circuit at t equal to infinities in this picture, it would be like this. Okay, so therefore your Vc at infinities is equal to Vs, right? Because there's no current flows, I equal to 0, no current flows. That means there's no voltage drop across this, no voltage drop, right? No voltage drop, 0 volt. So therefore this point is the same thing as this point. This point is same as this point. So therefore it's equal to Vs. Okay, what about this one here? Okay, what is this circuit? This is Vs, this is R, right? The current IL. For an inductor, if, well, this is apparently it's DC signal, right? DC values. So IL would be constant. At t equal infinities, IL would be constant for sure. Okay, so if IL is constant, no changes in current going through inductor, an inductor would behave like, I hope you can answer it in your head right at home, right? Short circuit. So therefore, your IL at infinities, right, at infinity would be equal to simply Vs over R. So do you see this? Look. So nice. Vc at infinity is Vs, so therefore it's right here and right here. IL at infinities is Vs over R. It's right here and right here. So do you see the pattern? See this pattern? So the pattern is, right, Vc of t would be Vc at infinities plus Vc at 0, right, if the switch changes to 0, minus Vc at infinities, E minus T over tau. In this case, IL of t is equal to IL at infinities plus, right, IL at 0 minus IL at infinities e minus t over tau. So in other words, whatever you were asked, it would be x at the final values, right, plus x at initial minus x at final values, okay, e minus t over tau. So it seems that if you have RC or RL circuit, so first order circuit, okay, your answer would be in the form of this. And the three values you have to find, right, at infinities, initial values, and tau, and you get the answer, right? So therefore, I'm going to end it right here. Next sessions, we will talk about how to find these values, doing it by, using step by step. Okay, so thank you very much for today. Have a good day. Bye.